Hello, welcome back to Introduction to Chemistry. This is our last week. We are almost there, and this is the second to last online lecture number 22. So the week before, we discussed a lot different chemical reactions. So we learned about substitution reactions and elimination reactions. So both of these reactions are based on a nucleophilic attack on a halogenoalkane. So, and what reaction pathway we have depends on the structure of the halogenoalkane. So in this table, I'm listing three different structures of halogenoalkanes, with X being the halogen. So a primary halogenoalkane has very little substitution, only this one alkyl group attached to the halogen, and that's why such a primary halogenoalkane prefers an SN2 or an E2 reaction. That means that both the nucleophile and the halogenoalkane, they need to meet to undergo the reaction in a single step, but the rate law depends on both concentrations. And the reason for it is that this primary halogenoalkane cannot form stable carbocations, and that's why it proceeds via SN2 or E2 reaction mechanisms. So now, whether we have SN or E depends on whether we have a regular nucleophile, such as a bromine or a cyanide, or whether you have a base. Base like sodium hydroxide or ammonium, they cause elimination reactions, while regular nucleophiles cause substitution reactions. So the secondary halogenoalkane, it is not really 100% clear which reaction pathway it can take. It can be either of these four, because there is kind of a competition between stability of the carbocation and direct reaction with the nucleophile. So you cannot really say it's somewhere in between, but again, if you have a regular nucleophile or whether you have a base determines if you have a substitution or an elimination reaction. So the tertiary halogenoalkane, this one allows for the formation of stable carbocations, and that's why you have either SN1 or E1 reactions. So again, base determines elimination and a regular nucleophile a substitution reaction. So this week we start with a discussion about reactions with alkanes, alkenes, and alkynes. So what is the difference between alkanes, alkenes, and alkynes? So an alkane is made up of only sigma bonds in red here. These are two carbons and they are both sp3 hybridized, and those form three sp3 sigma bonds to the surrounding groups. On the other hand, alkenes, the carbons are now sp2 hybridized. So they can form three sigma bonds, but additionally one pi bond. And the pi bond results because of the p orbital from each carbon overlapping, forming the pi bond. The third candidate is an alkyne. So an alkyne has per carbon only two sigma bonds and additionally two pi bonds. That is because the carbon is now only sp hybridized, and the two pi orbitals that form result from two p orbitals from each carbon. So for an alkene, the angle between these two sp2 hybridized groups here is 120 degrees, and for an alkyne, the angle between the two sigma bonds here is 180 degrees. So you can measure the bond dissociation energy for an alkane, and you found about 343 kilojoules per mole. On the other hand, because an alkene is composed of here both a sigma and a pi bond, you have a higher bond dissociation energy of 612 kilojoules per mole. For an alkyne, you have three bonds to be broken, and that increases the bond dissociation energy to 838 kilojoules per mole. See that the sign of the bond dissociation energy is always positive. That means energy has to be introduced in order to break the bonds. So for an alkane, the two alkyl groups that are connected here, they are only connected through a sigma bond, and therefore it can rotate freely. The two methyl groups here, they could rotate very freely without there being any energy penalty. On the other hand, for an alkene, because of the spatial arrangement of this pi bond, rotation around the central axis is hindered. It would require the pi bond to be broken, and that usually happens only at high temperatures. So because of that, for alkenes, unlike for alkanes, you have so-called configurational isomers. So for instance, here you see one configurational isomer, a Z-but-2-ene, right? So here the two methyl groups are both aligned on the top half of this molecule. On the other hand, the other configurational isomer is here E-but-2-ene. So now the two methyl groups are in a diagonal position and they are on opposite sides. So this configurational isomer, you see these two methyl groups, they are very bulky because the orbitals of the hydrogens are occupying space, and that causes these two methyl groups to have some overlap, and that causes some so-called steric strain. And the steric strain is energetically costly, and therefore it makes this configurational isomer less stable. On the other hand, here there is no such steric strain because the methyl groups are on opposite sides and therefore not in contact with each other, and that makes this configurational isomer more stable. So, but it's not just steric effects that govern the stability of alkenes. There are also electronic effects. So here you have an alkene which has this side methyl group, and now the sp3 hybridized CH bond here, it can actually have some overlap with this empty pi star orbital, the anti-bonding pi orbital. And that happens again through hyperconjugation, and this hyperconjugation increases the stability of the alkene. And also you can have a delocalization of the CH bond here. So the pi bond can donate electron density to the end carbon here, and then the hydrogen can donate electron density to the middle sigma C bond here, and that can cause the hydrogen to actually split off as a proton, making the end group here negatively charged. So this is some form of delocalization, and you learned before, delocalization always increases stability because it reduces the energy. So here, in fact, the proton, it does not really split off and go into the environment. It stays very closely connected to this carb anion. So from this you can understand now that the alkene with the highest degree of R groups is the most stable. So if we now decrease the amount of R groups, we get less stability with the least stable alkene that has only hydrogen substituents, but the most stable, the one with the most R groups. So alkenes and alkynes, they undergo so-called electrophilic addition reactions. So no substitution and no elimination reaction, but electrophilic addition. So why is that? It is because the alkene and alkyne bond, it has very high electron density between the two carbons, and that makes itself a nucleophile basically. So it can react with an electrophile, for instance an cation, to give a carbocation. So here's the reaction. The electron-rich double bond here carries out a nucleophilic attack on this electrophile, and it forms, by addition of the electrophile, a carbocation here now. So this carbocation itself can now be the victim of a nucleophilic attack with an addition of a nucleophile to the cationic site, forming this new added molecule. Same thing for the alkyne, only that now you have a triple bond here, and which is also rich in electrons and therefore can attack an electrophile and forming again a carbocation with the added electrophile, but this time we have a still remaining double bond here. But nevertheless, this carbocation is also susceptible to a nucleophilic attack that then adds to the molecule. So this is called an electrophilic addition reaction. So what determines the nucleophilic strength of an alkene or alkyne? So here's a typical alkene with 4 methyl groups, and as a comparison I have here a fluoroalkene with 4 fluorine groups at the side. So you can probably remember that fluorine is more electronegative than carbon, and therefore it is a so-called -I group, a negative inductive effect that occurs. What that practically means is the high electron density in the double bond region here is drawn towards the fluorines, and that causes these region to be less electron dense. On the other hand, the methyl groups here, they are less electronegative, they are +I groups. So what they do is they actually donate additional electron density to the double bond region here. So what that means, because now the double bond region is not so rich in electron density anymore because of the electron withdrawing fluorine groups, this here is a weaker nucleophile because it is not as willing to donate electrons anymore as it would be in the case of the only methyl substituted alkene. Here you have this high electron density that makes it very nucleophilic, making it very willing to donate electron density. Okay, that's it for this online lecture. Next time we continue with reactions of alkenes.